Talk is by Ramon van Handel, and this title is Strong Convergence and Services.
All right, thank you very much. It's really a pleasure to be at this nice meeting where I got to meet many new people and see old friends and learn a lot of interesting mathematics. So I'm going to talk about a joint project with Michael Maggie and with Doron Puder. And it's about strong convergence. And strong convergence was mentioned in the talk by Ewan, but it wasn't really discussed. And so I thought I would give a mostly kind of non-technical talk where I talk about strong convergence and a little bit what kind of applications it has and what you can do with it, and lead up and try to motivate our main result here. And if I have time at the end, I will try to very briefly explain the kind of difficulties that we face. So let me start with stating a result in random matrix theory, which is one of the results that motivated a lot of research work, recent work in this area, which is a result due to Bordenov and Collins. This was a very important result in this area. So let's take a set of independent, uniformly distributed random permutation matrices just n by n permutation matrices, just draw them independently and uniformly at random. And what we're going to do is we're going to take these permutation matrices, we're going to take non-commutative polynomials of them. So I'm going to call a star polynomial is just a polynomial, a non-commutative polynomial in these matrices and their adjoints. And then the statement is that for any star polynomial P, we can compute the operator norm of the polynomial of these permutation matrices with a little twist. So I'm taking the norm of the non-commutative polynomial of these random permutation matrices. But there is a little caveat, which is, these permutation matrices always have the fixed point. The all ones vector is always a fixed point of the fixed vector of the permutation matrices, right? If I permute a bunch of ones, I just get a bunch of ones back. So this is like the trivial eigenvalue of these kind of polynomials. So I'm interested in spectral gaps, so I'm going to remove it. So we're going to work on the orthogonal complement of the fixed vector. And the claim is that the norm of any such polynomial converges. Continue to the next line, converges as the dimension of the matrices goes to infinity to the norm of the same polynomial of the regular representation of the free group. Operator norm.
In the usual, in the standard representation.
In the standard representation, exactly. Because I removed the fixed vector, right? I removed the trivial one, so it's a standard representation. I take the operator norm. This is the operator norm. This is the regular representation of the free group. And these are just the free generators. So this theorem allows us to compute for a very large class of random matrices, any random matrix that can be formed out of as polynomials of, so star means that a polynomial of these guys and their adjoints. We can compute asymptotically the norm of these kind of random matrices. So a more group theoretic way of viewing it. So here's another viewpoint or another formulation. Just so we're all on the same page. So we can just view these matrices as arising from a representation of the free group. Okay? So we can take phi n to be a homomorphism from the free group to the symmetric group on n with n on n letters. And this phi n will just send any generator of the free group to the corresponding permutation. I'm being a little informal here because I said this was a permutation matrix, but of course a permutation matrix is identified with the permutation that defines it, right? So it sends the generator to the Kate matrix. So this is a random homomorphism. And using this homomorphism, we can construct a unitary representation of the free group, right? So what do? We go from the free group, we take this homomorphism, which maps us into Sn, And then, as was pointed out by Uri, we take the standard representation, which maps us into un minus 1. We've constructed here a random unitary representation, right, of the free group. And then what this theorem is saying is that this random unitary representation is converging in the following sense, right? So the theorem says that if I take the norm of pi n of any element of the group algebra, it's converging as n goes to infinity to the norm in the regular representation. There should all my limits are going to be, so I don't want to keep writing it, but thank you for are going to be in probability. And similarly here. So, for those of you who are not probabilists, that just means that the difference between that and that, the probability that's greater than epsilon, converges to 0 for every positive epsilon. That's converges to 12. So one can also talk about almost sure convergence, things like this. I'm going to sweep all of this under the rug. That's a separate issue. Okay? So we're just doing convergence. So, we've seen a lot of talks about property T, right? Property T says that for every representation of a group, we get a spectral gap. This is in some sense the other opposite niceness, right? Because here we're saying we have a very, very, very nice sequence of representations, these random ones, but they behave asymptotically like the free group. Since they're kind of these are finite dimensional representations that are asymptotically tempered. That's basically what we're saying. And so this theorem of Borden-Van-Collins guarantees that not only do such representations exist, but in fact they can be generated using permutation matrices. Is it okay? So that's and this notion of convergence is called strong convergence. So we will say that these random representations converge strongly to the regular convergence. So what is the history of this theorem? So this wasn't the first theorem along these lines that existed. So the origin of this is in the work of Hagerup and Torbjornsen. And also Collins. So this was around 2005 it appeared, this was like 2014. And what they studied is they studied a very similar question, but rather than taking random permutation matrices, they just studied random unitary representations of the free group, right? So you just pick, rather than picking these to be random permutations and then composing them with the standard representation, you can pick random unitary matrices. Right? From some model, maybe uniform, maybe not uniform, in the case of Hagerup and Torbjornsen. And you can ask for the same strong convergence, and this is easier to prove. It was proved earlier, and this had beautiful applications in the theory of C-star algebras. So the original motivation for studying this, that was actually the question was asked by Voiculescu around 1993. The original motivation for studying these kind of questions was for applications in the theory of C-star algebras. And for that, it's enough to have just unitary representations. But somehow or other, this theorem of Borden-Van-Collins, because it's working with permutations, it has a more discrete flavor. And it turns out that this discrete flavor is extremely useful for applications in random graphs, in geometry. In these kind of applications, you really want to have these permutations. You want to have these more discrete sets. And so this theorem of Borden-Van-Collins led to a lot of interesting developments. So I want to give some examples. So the first example of something that comes out of this theorem is a theorem that was already known. This is Friedman's theorem, which was mentioned several times. But we should understand that this is a special case of the theorem I've just written down. So Friedman's theorem says that if I take a random regular graph of some fixed degree, some fixed degree, then the spectral gap of it converges to what you would expect to the spectral gap of the infinite regular tree. Okay? So how does it arise? Well, what we will do is we will take these permutation matrices plus their adjoints. So here's a wonderful random matrix. So each of these permutation matrices has exactly a single one in each row and column, right? So if I add them up with their adjoint, I have a adjacency matrix of a 2R regular graph. This is the adjacency matrix of a 2R regular graph, the random one, of a random 2R regular graph. And we want to understand the spectral gap, right? So a 2R regular graph has a trivial eigenvalue, which is 2R. But that's exactly the one whose eigenvector is the all ones vector. So if I want to understand the spectral gap, I'm going to remove the trivial eigenvalue, and I'm going to look what the other eigenvalues are. So we just remove the trivial eigenvalue. And we're starting to look a lot like that, right? So here is one very nice polynomial, it's just the sum of the generator. And what the theorem says is that this will converge as n goes to infinity to the norm under the free group of the following element of the group algebra, which is just a Laplace. And if you check what the definition is of the regular representation, this is just the adjacency matrix of the 2R regular tree. Right? So Keston, in 1959, computed this as 2 square root 2R. So this is exactly the statement of Friedman's theorem. Okay? But you see, it's this very special case of this theorem, but for one very special choice of this polynomial. So that's, at least we have reproduced one very non-trivial theorem as a special case. But the point here is that because I can choose any polynomial, I can encode many, many more models into this theorem, right? So I have a choice of an arbitrary polynomial, so I can try to take other kinds of, for example, random graph models, and try to encode them as some more complicated polynomials of these permutation matrices and try to understand whether we can understand their spectral gaps. Does that make sense? So that was indeed the original motivation of, I should not use these boards, right? So I'll just go back here.
You can do the top one.
Okay. So I'm slowly working my way towards the results that we're interested in. But let me give you the kind of main application in the paper of Bordenov and Collins, which was actually a conjecture of Friedman. So it's something that was conjectured by Friedman of Friedman's theorem. So this is a statement about random regular graphs. But can we make natural models of random graphs that are not regular? So, you know, each non-regular graph could have a difference. So here the 2R regular tree shows up because it's the universal cover of any 2R regular graph. If I take a non-regular graph, it can have kind of, the universal cover will still be a tree, but it will be some, for every graph you'll get a different tree. Right? So what is a natural model? So Friedman proposed, I think the model is due to Friedman, though I'm not 100% sure. So proposed to do the following. Let G be any finite graph, let's say a simple graph. So if I fix a graph, it has a universal cover, that's a tree. And now I want to create a sequence of graphs that have the same universal cover. So the natural way to do this is to form finite sheeted covers of this fixed graph. Okay, so let Gn be an n-sheeted covering space of G, just in the sense of topology. I'll construct them in a moment, or at least I'll draw a picture in a moment. So by construction, these n-sheeted covers have the same universal cover as the original graph. Now the question is, as we let n go to infinity, do we get a nice behavior of the spectral gap? So what Friedman conjectured is that if I pick these at random, if I randomly pick one of all the possible n-sheeted covers, then as n goes to infinity, I will qualify it in a moment, but roughly speaking, the spectral gap of these covers should converge to the spectral gap of the universal cover of G. There's a little asterisk, which is that if I have any eigenvalue over here, any eigenfunction over here, and I just lift it to the cover, of course it will still be an eigenfunction of the cover. So I can never, if I have a bad eigenvalue over here, I can never destroy it by taking a cover. So when I say spectral gap in this setting, I mean that the new eigenvalues that are generated in the cover are controlled by the universal. So this theorem was proved by Bordenov and Collins. then the relative, I'm writing it very informally, so the relative spectral gap. So the upper bound of the new eigenvalues converges to what you will get from the universe. So this was a conjecture of Friedman. It was proved in the paper of Borden and Avocalis. And the question is why, what does this have to do with random permutation? So you have to understand how to generate covers of a graph. So let's do an illustration. Everybody can still see when I write here? So let me pick some simple graph here. Here's G. And how do I construct covering spaces of this graph? So what you're going to start by doing is you're going to start by fixing some spanning tree in this graph. So for example, in this case, these three edges form a spanning tree. So those yellow edges form a spanning tree. Now suppose I want to generate a three-sheeted cover. So here I'm going to try to generate a three-sheeted cover. So what I'm going to do is I'm going to copy this spanning tree 3 times. So let me attempt to do it in a useful way. So here's once, here's twice, here's another time. Right, so I have 3 of these, 3 copies of this spanning tree. And each of them is missing 2 edges in the original graph. Right, those 2 edges. So what I'm going to do is I'm going to draw these edges in here, these missing edges, I'm going to draw them in here, but I'm going to randomly permute which copy of the spanning tree I attach them, right? So for example, this guy should be attached to one of the middle guys, but rather than attaching him over here, I will choose a random permutation of these 3 copies and I'll attach it to the corresponding vertex of the permutation. For example, I could attach this guy here, and then the guy corresponding here I could attach here, and then the guy here I could attach here. Right? So that would be the permutation 1, 2, 3. And then I have the other missing edge, right? So here, for example, I have a missing edge. So, for example, I could take this guy and I could do the permutation which has 1 as a fixed point and switches 2 and 3, right? So then I could attach this one here and this one here. Well, now I've created 1 cover. So this is a recipe. Right, so you fix the spanning tree, and now the remaining edges, you put them in, but you randomly permute which of the copies you attach them to, or you permute them, right? So any cover, any 3-sheeted cover of this graph can be represented in this way, for some choice of permutation. And if I choose my permutations, my 2 permutations, 1 for each missing edge randomly, I will get a random 3-sheeted cover. So these graphs, they are really defined by a set of permutation matrices. Does that make sense? And so the question is now, what is the adjacency, right? We want to understand exactly the same thing here. We want to understand something about the adjacency matrix of those graphs. And the kind of point, which I'm writing again informally, is, roughly speaking, the adjacency matrix of this graph Gn can be expressed as a polynomial of these random permutation matrices that define it. To be entirely precise, it's a polynomial with matrix coefficients, but there is a kind of standard tensorialization trick that reduces bounding the norms of those guys to bounding the norms of ordinary polynomials. So those things follow also from the... So you see here we have a much more complicated model because I can start with any finite simple graph and construct these more complicated model of random graph. And, but the point is that because I have a choice of arbitrary polynomial, I can encode the adjacency matrices of these graphs as some polynomial of these random permutation matrices, and therefore I have here immediately a tool, right? As soon as I've done this encoding, I can hit it with this theorem and I know what it converges to. And then I just have to be careful to interpret the limiting operator as the Laplacian on the universal cover of this graph. So that was the main application in the paper of Borden and Avocalis. So far, so good? So if you can do this for graphs, then it would be really great if you could do it also for manifolds. And this is motivated by actually very old questions in spectral geometry. This was a big breakthrough by Hyde and Nagy. So the third example here. So let's try to play the same game as over here, right? So, but rather than starting with a graph, let's start with a manifold. Let's start with a manifold that has a nice universal cover that has a spectral gap. So, let M be a hyperbolic N manifold. So its universal cover is the hyperbolic N space. And the question is whether if we take the Laplacian on this manifold, so we want it to be finite volume. And the question is if we take the Laplacian on this manifold, well, it is what it is, right? But we would like to know if we make this manifold larger and larger, whether the spectral gap of the Laplacian will look like that of the hyperbolic plane. Okay? So that's the exact analog in some sense of the question over there. And that gives you a way of constructing manifolds with very beautiful spectral properties. Very nice spectral properties. So we can try to do the same thing. So let Mn be an n-sheeted cover. And then the question is it true that let's say the relative spectral gap, in the sense that I explained it before, of the Laplacian on these n-sheeted covers, or can I find a sequence of n-sheeted covers so that the relative spectral gap of the Laplacian converges to that of the spectral gap of the hyperbolic n space? That would be the analog of that question over there for graphs. Now we're doing it for men. Is it good? So it's a very general question, right? Is it true? Can one find a sequence of covers? Is it true for many covers? How do you do it? But now it's not so obvious. Okay, so here, I mean, I didn't write down the formula, but there's a very simple formula for the adjacency matrices of these graphs in terms of the permutation matrices. Here, in first instance, the Laplacian is a continuous object. It's really not clear what this has to do with strong convergence. But Hyde and Nagy, they basically discovered a way of connecting the spectrum of the Laplacian to the spectra of polynomials of the random permutation. So, okay, so the construction of the cover here, in some sense, the picture you should have in mind is it's kind of similar to over there. So if I have a hyperbolic manifold, you can think of it as a quotient of the hyperbolic n space by some group acting on it, right? So it has a fundamental domain. So I could get the manifold itself back by gluing the facets, right, of the fundamental polygon. But now if I want to construct, let's say, a 3 cover, I take 3 of those fundamental polygon and I randomly scramble which of their facets I hook up to each other. So I glue to each other, then I get a cover.
So the randomness again will be by product of permutation groups?
Exactly. So now what we want to do is we want to now just randomly choose, okay, which facets of the fundamental polytopes we connect to each other. That's the hope, right? Unfortunately, there's a problem because over there you see no matter what permutations I chose, I still get a graph. But if I take, for example, let's say, hyperbolic plane, and so I have a polygon, and I randomly glue together the edges of 2 copies of this polygon, I mean, what happens to the vertices? If I'm not careful, I'm going to create singularities at the vertices. I'm not going to get a manifold, right? So the problem is that now it's no longer legal, right? It's no longer legal to choose any permutation matrix. So roughly speaking, I mean, I'm writing it down as a very general statement. They were working in dimension 2, but I mean, their techniques, I think, are very, very general. Roughly speaking, the answer is yes. if you are choosing your permutation matrices in a way that will create a manifold. And what is that way? If the pi n you choose, right? So we're going to again choose a representation, right? But the point is that pi n, right? So pi n is now going to be the standard representation composed with phi n, but unlike in the previous case, phi n must be a homomorphism not from the free group, but from the fundamental group of the manifold you studied. So the condition, the correct condition for this gluing construction to actually give you a cover is that the permutation matrices that you choose satisfy the relations of the fundamental group. Does that make sense? This is a known fact that you can find in topology textbooks. I'm not saying I knew it, but for example, it's in Hatcher. So it exists out there.
Is that and if you have some convergence?
I beg your pardon?
The answer is yes, if you have some convergence and this.
Thank you. So if the representation is a representation of gamma, and phi n converges to the regular representation of the fundamental group strongly. So Hyde and Nike have this machine, okay? They understood how to, they understood how to connect the spectrum of the Laplacian to strong convergence. I mean, very roughly speaking, what they show is that if you take the resolvent of the Laplacian, it is not itself a polynomial, but it can be approximated by polynomials of these permutation matrices. And that makes a connection between the spectrum of the Laplacian and the spectrum of the permutation matrices, okay? And that's the connection of strong convergence. So this is something that is true in a general setting. I mean, you know, there may be some technicalities in implementing it, but the technique, the basic technique here has nothing to do with surfaces or anything. The difficulty here is that now we no longer necessarily have a free group. Right? So if we just have Bordenave and Collins, then it's useless, except if you happen to start with a manifold M whose fundamental group is free. And that's exactly what they did in their original paper. So Hyde, Nagy, they chose M such that the fundamental group is free. For example, you can take a sphere, a two-dimensional sphere, and punch r+1 holes in it. And you get a hyperbolic manifold, finite volume, whose fundamental group is free. That's exactly Fr. And then you can apply this machinery, and then you will see that that's random, right? By the theorem of Bordenave and Collins. If I pick uniformly at random an n-sheeted cover of this manifold, then I'm going to get a sequence of covers, right, that have more and more of these cusps. And if I look at the Laplacian, its relative spectral gap converges exactly to that of the hyperbolic two-plane, which is 1. And even the existence of such manifolds was a long-standing open problem. Right? So that settled an old conjecture in this area about surfaces. It's good? But now, of course, we have the obvious question. Which is, now that we have some motivation to think about it, we really don't want to think about manifolds whose fundamental groups are free. They're kind of boring, right? I mean, or at least there are very few of them. So the obvious question is now, okay, what if the fundamental group is not free? So, what if gamma is not free? And there are really two questions. Does there exist, even, a sequence of pi n's? By pi n, I mean permutation representation, right? So representations of this form, okay? That strongly converges to the regular representation. And secondly, if so, right, is this behavior typical? Which means that if I pick such a representation as over there uniformly at random, right, does a typical representation have the property that converges strongly to the regular representation? It's a stronger property. Does that make sense? One of them asks for existence, the other one asks, do almost all of the representations maybe satisfy this condition? It's a very strong one. So,
Representation is a permutation.
so we are looking exactly for this situation. So we're picking, you see this is a finite group, right? So there's going to be a finite number of choices because we have, okay, these are finitely generated groups, so we have to just pick which permutation matrices are generators. There's only a finite possible options, so you can pick a homomorphism. I'll give in a moment an example which makes this very concrete. Okay, so does it make sense? So this question, of course, sets you off in some very beautiful direction, and Michael tomorrow is going to give a talk going in all sorts of directions with this question. Is that okay? Good. Michael will say yes. So, but I would say that so far, you know, there's one case that we really understand very well, which is the case of surface groups. Okay, so the rest of the talk, and that's the result also I'm talking about. So the rest of the talk, I'm going to talk about surface groups. So now we take M to be a closed, orientable surface of genus G. So fundamental group of M is now the surface group of genus G. This is the surface group of genus G. So, for example, I mean, not much of a loss of generality. Let's look at the fundamental group of surfaces of genus 2. So this is a group, it has 4 generators. And it has one relation which says that the commutator of A and B times the commutator of C and D is the identity. So this is a one relator. Does it make sense? And now just to make very concrete what we're trying to achieve, okay? Because I mean, now I went here to representations, but actually, you know, my background is in probability, so you know I'm pretty down to earth. Like, you know, I can phrase this very explicitly. What are we trying to do? We're trying to find a model that samples 4 permutation matrices from some distribution. And what does the model need to satisfy? Well, those 4 permutation matrices have to satisfy this relation, right? So we want to construct some, let's say, let me call them AN, BN, CN, and DN. These are just n by n permutation matrices, right? That satisfy this relation. Is the identity, right? And that you have strong convergence, which means that every star polynomial of these 4 permutation matrices converges to the corresponding star polynomial of the regular representation of the surface group applied to the standard generator. Is it okay? So that's the question 1 is, does there exist a sequence of such permutation matrices? And question 2 is, what happens if I sample 4 permutation matrices uniformly at random from the set of all 4 tuples of permutation matrices satisfying this strange condition over here? So, you know, in probability theory, we used to study independent things. I mean, this is a completely weird model. This is insane. Nobody would write such a thing down unless you had a reason. This is a very strange model of random permutations, but that is what a typical right? That's what a typical homomorphism from the surface group to the symmetric group. And now the question is, how do these very strange random matrices behave? And you notice they're not independent because they have to satisfy this relation of probability 1. This is a very strange dependent model of random matrices from the point of view of probability. Is it okay? So, it turns out that the answers to both questions 1 and 2 up there are yes. Okay. So in this case, for surface groups, 1 and 2 both have the answer yes. Of course, 2 implies 1, so that's a tautology. But So the answer to question 1, let me write it like this. The answer to question 1 up there is yes. Due to Lauder and Maggie. What they did is they found a way to reduce this problem back to Bordunov and Kohler. So the way they do that is they use the fact that surface groups are limit groups. So they can be somehow locally, finite balls of surface groups can be embedded into the free group. So you can, what you can do is you can choose your permutation matrices here to be certain words in independent random permutation matrices that are forced to satisfy this, that satisfy this condition already, right? I can choose some certain specific words, long words, in IID random permutation matrices so that those words satisfy these relations. And that way you can map the structure of the surface group into the free group locally. And if you do this very carefully, then you can deduce strong convergence of that model of the random matrices A, B, C, and D. This is a highly non-uniform model, right? This is a model that has a very strange distribution. So this tells you that there exists a sequence of these representations, but it doesn't tell you anything about whether they're typical, right? Whether all but a vanishing fraction of these representations have this. And the main theorem for this talk is that the answer to 2 is also true. So this is with Michael Doron. Myself. So what it says is a fraction 1 minus lambda 1. So with probability going to 1, if I sample randomly uniform of permutation representations by n of a surface group, converges strongly to the regular representation. G, sorry, not the free group, surface group. So that means that not only is this behavior, do there exist such representations, but in fact they're typical. Right? If I just grab one out of the bag, I will have increasingly large probability that I'll get something that converges to the regular presentation. There's a little addex. Yes?
The previous proof also used randomness, but
Exactly.
it wasn't uniform.
Exactly. So we don't really understand this model of randomness. So what you do there is that each A n, B n, C n, and D n is a word, so it's a product of many of these independent random permutation matrices. They're not all independent, right? It's some very long word, and the words get longer and longer as you increase n. And at least I don't really understand what this random model is. We don't really know what this is.
Is it potentially?
I highly doubt it. No, I know it's not uniform. What I don't know is whether in some sense the distribution becomes more uniform as n increases. However, it's not even clear how to quantify that because the dimensions get bigger, right? So it's not even clear what that means. Moreover, this happens at a rate. Right? So we have convergence, and so far I haven't said anything quantitative, but in fact we of course have a rate of convergence here. And it happens at a rate that is polynomial in it, which turns out to be interesting. So that's the main theorem. How am I doing? Very good. And now, if you have this, then you can immediately plug this in to the machinery developed here, and you will get that all but the vanishing fraction of the n-sheeted covers of any closed orientable surface has an optimal relative spectrum. So that's an immediate corollary if you plug it into the machinery developed over there. So I'll attribute it to us, meaning that we successfully plugged it into what they did. Okay. But in fact, one can do a little bit better. So the statement is that for any closed orientable surface fraction 1 minus little o 1 of all n-sheeted covers Mn has the relative spectral gap of the Laplacian converging to that of the Laplacian in the hyperbolic plane. Spectrum in the Laplacian hyperbolic plane is just interval 1/4 to infinity, so it means all of the new eigenvalues of these covers, right, they asymptotically converge, they're asymptotically greater or equal than 1/4. This part follows, that part follows immediately from plugging this theorem into the methods of Hyde and Mackey. But there's a moreover. The convergence is at a polynomial rate. And this is the part that's new over here, because the original arguments over there, you know, one has to encode the spectrum of the Laplacian into a strong convergence problem. The encoding works for polynomials, but in the original argument, they had to take those polynomials of higher and higher degree. And it kind of messes up the quantitative features of this problem. And Hyde, Massera, and Thomas found a kind of a variant of the argument that was used over here that was more efficient, that allowed them to translate the polynomial rate that we get over here to a polynomial rate also for the Laplace. That needed an extra.
But it's a consequence of the theorem above.
It's a consequence. So the first part of this corollary is a consequence of the theorem above plus what Hyde and Mackey did. The second part is also a consequence of the theorem above, plus a variant of what Hyde and Mackey did that allows you to transfer better the qualitative property. Basically, rather than using the resolvent, they designed some very special function of the Laplacian, so that it turns out that that function already is a polynomial of the permutation matrices. You don't need to truncate it, and that fixes the convergence. Okay. And the reason I insist on this polynomial rate is because in this business of surfaces, so this has nothing to do with strong convergence, but there are these long-standing conjectures. This is a very active field, random hyperbolic surfaces. There are long-standing conjectures coming from physics about quantum chaos. And these conjectures from physics, they predict that the bottom of the spectrum, right, the bottom of the spectrum of the Laplacian hyperbolic surface, due to quantum chaos, the eigenvalues should behave like the eigenvalues of random matrices. And like standard random, like GUE random matrices, and Gaussian random matrices. This is a prediction from physicists. Nobody knows how to prove this. Okay? But if you believe in that prediction, then the rate over here that you should get is n to the minus 2/3. And no other construction until this point was able to get even a polynomial. Okay? So this polynomial rate is expected from kind of conjectures in quantum chaos. But this was really the first model in which such a rate was observed for random hyperbolics. And there's a whole development around this about other types of models of random hyperbolic surfaces. So I don't want to get into it now. I have like 5 minutes left. So, but this polynomial rate is a kind of interesting feature of this. So, I spent almost my entire talk motivating the results, but I want to say a few words about what goes into this theorem. You know what? Let me start back. So, I think it's fair to say that if you had asked 2 years ago how close one is to proving such a theorem, it would have been completely out of reach. But what happened in between is that, not in this context, but with another set of co-authors, Anthony Chen, Jorge Garza Vargas, myself, we discovered a new method of proving the Bordenov-Collins result. So for independent random permutation. It's called the polynomial method. And we used this originally to reprove the Bordunov-Collins result, but in a much, much simpler way and with with this polynomial rate, which was not available in the Bordunov-Collins result either. So the proof of Bordunov-Collins is quite difficult, and it uses a lot of delicate estimates and delicate machinery that's very specific to the free group. So it was kind of surprising that we found a soft method of doing it. So this method is kind of soft. It doesn't really use many features of the model itself. So this soft method also made it possible now to think about other kinds of problems like these problems over here, which are not even free, and we don't really have a hope of doing very, very delicate computations. But using this method, there was kind of a hope of approaching. So, but initially we didn't develop this method for these kind of problems. We developed a method just for the free case, for the independent random permutation. And, you know, explaining how the method works exactly is really a different talk. Okay, so I would give you another talk now for an hour about how this method works. But let me point out the key feature. In the setting where you have independent random permutation mix. So in the Bordunov-Collins setting, independent. So the starting point for the method is the following observation. So let me give some names to these things. So we're interested in polynomials of these matrices, so let me give them a name so I don't keep writing the same thing. Okay. Self-adjoint. Or even let me just remove the indicator. Self-adjoint. And the limiting object, let's call it x infinity, though I won't need it really. This is the regular presentation, right? So, you know, rather than keep writing these long things, I just called xn the polynomial. I'm interested in x infinity as a limiting object. And now this is a polynomial of permutation matrices. Where is it? This is a polynomial of a bunch of independent permutation matrices. You know, that's a very simple model. Right? So, if I want to compute, for example, the expectation of this polynomial, then I just have an expectation of the entries of a bunch of permutation matrices. All I get is the expectation of a product of entries of a bunch of random permutation matrices. That's a combinatorial problem. I mean, you can just sit down and compute it, right? It's a kind of combinatorial exercise to compute the expectation of a product of 3 entries of a random permutation matrix. So, if you were to do this, what you would realize that if you take the expected trace. Now here I'm taking a polynomial, so I'm just composing of degree, let's say q. So I take a polynomial of this matrix xn, right? So this itself is a polynomial, so I just get this xn is itself a polynomial of the entries of these permutation matrices. So I've written here just the expectation of some complicated polynomial of the product, right, of the entries of the matrices. And it turns out that this is a rational function of 1 over n. Also of degree q. So it's a ratio of 2 polynomials of degree at most. Now it's a very complicated rational function. Okay? I'm not saying that we understand what it looks like. I mean, that's one of the problems in the usual ways of dealing with random matrices. Yeah, I can write a formula for it, but it's some huge sum over some combinatorial object. How do you estimate this thing? I mean, it's a delicate business, right? But it is a rational function, and that's a soft number. And in particular, right, that means that we can understand the limit as n goes to infinity. We understand what happens. Well, there's the value of this at 0. Let's call it mu0 of h. There is the first order term, right, which this is a smooth function. So it's a rational function. It doesn't have a pole at 0. So, it has some obvious behavior that's all smooth functions. You can say this. So what we realized is that you can actually exploit the fact that this is a rational function, it's a ratio of polynomials, not quantitatively, but qualitatively. Because what do we want to do? We want to have some kind of bounds on these terms that appear in this expansion. But notice that, for example, nu1, just to give an example, nu1 of h is just a derivative of this rational function at 0. So this coefficient is just a derivative of a polynomial. It's a ratio of derivatives. Right? It just involves some polynomials in the derivative. And for polynomials, we have beautiful inequalities that come from the 1800s, from the late 1800s, that allow us to bound the norms, it allows us to give bounds on the derivatives of polynomials in terms of the polynomials themselves, in terms of the maximum of the polynomial itself. And this gives us a kind of analytic tool to study these coefficients over here that we wouldn't have if these were not polynomials. So we can now import tools from the analytic theory of polynomials which give kind of for free very strong bounds on these coefficients, let's say mu k of h. And they're just using the fact that because these are polynomials of bounded degree, they cannot vary too much. A polynomial of bounded degree cannot go like this, right? It has to kind of vary smoothly. So we're just using this very soft fact. And how we use it, of course, is the trick, so I don't have time to go. But now let's go to this model over here. So now we go to this surface group model. Now we have this very strange model where we condition on this relation being true, right? And the question is this still true, right? Is it still true that you have such an expansion? And this surface group model was studied by, was already studied before us by Maggie and Buder a few years earlier. And there's good news. The good news is that they were able, using the representation theory of the symmetric group and various very clever things, to show that in this case, also, the trace statistics have this nice property that they behave in a regular way, u1 over n, u2h over n squared, etc. So they have some asymptotic expansion in 1 over n, just like you would expect from a rational function. This was achieved using the representation theory. I mean, it's a difficult story, but it was achieved using the representation theory of the symmetric group. The bad news is that these coefficients over here, they grow super exponentially as a function of k. Which means that certainly, most certainly, that function of 1 over n is not rational. In fact, it's not even analytic. This function is not even analytic. It's like it has a Taylor series with coefficients that grow faster than any exponential. It's not even an analytic function. So it seems like you're in deep trouble, right? So one of the kind of three, that we have kind of three ingredients to the proof. But the ingredient number 0, let's say, right? So it's number 1, if it's number 0 if you count 0, 1, 2, okay? But the first thing one has to do is one has to figure out whether this method can still be applied in a situation where you don't have rational functions. And remarkably, it turns out the answer is yes. So it turns out that to apply this method, one needs an extra ingredient. But to apply this method, you don't really need rational functions. All you need is that you have such an expansion with a kind of modest error term. As long as we can get such an expansion, let's say I go up to order q, q minus 1, q minus 1. As long as I have such an expansion with such an error term, divided by n to the q, which is huge, right? It's allowed to grow like any power of q factorial. These constants can be arbitrary. It's not for free, but it is something quite, this is not something that is so bad, right? So it turns out as long as you have such an expansion with a kind of modest error term, that this method still goes through. And once you have such an extension of the method, now you can apply it to much more complicated models. And then the two additional difficulties is one has to get such a quantitative version of the results that Michael and Doron got a few years earlier. And the other thing we need to understand, which I didn't talk about at all, is we need to understand some geometric group theory of what happens in the symmetric group. We need to understand if you have a random walk if you have a random walk in the surface group, we need to understand what is the probability that will reach a proper power. And that's, I didn't explain what this is needed for. That's needed to control this first order term over here, which is controlled by this. So these are ingredients that we already needed in the case of the free group. But in the case of a surface group, this required some new ideas. So let me end here. Thank you.
control of the probability of that an element reaches the proper power of himself?
So if you take a measure, a probability measure, U, on the group, finitely supported, then you can run a random walk with this, let's say symmetric. Okay. You can run a random walk with this step probability.
Yeah.
Does that make sense? So let's call little xn is the random walk with that step probability at time n. And what you need to show is that the probability that xn is a proper power, so let's say for some v in the group and k greater or equal than 2,
Yeah.
what you need to show is that the exponential growth rate of this is bounded by the what it would be in the regular representation. U. And the reason that this problem shows up, so this for the free group, this is something that was actually known, but in the surface group, yeah, okay, let me not go. You can ask me afterwards what is this. The reason this shows up is because it turns out that if I just take here a word, if I take the expected trace of a word in these random permutation matrices, now the question is which term over here is the smallest term? So this first order term only shows up if you have the identity. If you have any non-identity word, this term is 0. And it turns out that this term over here only shows up if the word is a proper power. So if you have a word that's not a proper power, this term is 0, and actually the expected trace is of order 1 over n squared, at least. And that's exactly what we need, because this is the normalized trace, so we're trying to beat the dimension. So we need that the dimension times this goes to 0, so we need this to be of order 1 over n squared. So we need to have some way of getting rid of this first order term, and that's where this kind of argument enters the picture. But if you ask me afterwards, I will explain in more detail how it enters the picture. But that is where it comes from.
So why do you have the convergence rate 1 over n to the c? Where is
Because this miraculous polynomial method is completely quantitative. Everything are explicit inequalities. So yeah, we get it gives you a polynomial rate for free, but I don't have an explanation why. It cannot be better than polynomial.
Yeah, but it's c is factored.
I'm not claiming any optimality about the C. And in this case, what will happen is that the C that we get for surface groups, the way, using the estimates we have, the C will depend only on the genus. So it's not going to depend on the polynomial or on, but it's going to, in our estimates, only depends on the genus. It's conjectured that the C should always be 2 short. So I think for any genus. So, but I don't have any hope of proving that using it. But these polynomial rates come from. Now, we didn't write it in the paper, but the method will probably work if an even worse bound here. If you have any 2 minus epsilon for epsilon positive, the method should still work. But then you lose the polynomial rate. So if you have something that has an even worse error term, at q to the q squared it breaks, that we know. But if you have anything better than a q to the q squared, probably the method will still work, but then you will not get a polynomial rate. Again, I don't know if that's real, but we don't have any example of a model that satisfies such a balance. I don't know how to test it.
Sorry.
Yes.
What about Z? If you take Z2 instead of gamma 2, what happens?
You mean abelian group?
Yeah.
Well, if you take
Or or another one relation group maybe.
If it's abelian, amenable, it's
yeah. So amenable you cannot.
Oh, I
Yeah.
see.
And if you take another one related group, it's an extremely interesting question, right? Because of course, it would be great to have such a statement for a 3-man, something else. And so in the analysis, which is due to Michael and Doron, the fact that it's a surface group, okay, what seems to be absolutely crucial in the analysis is that every letter here, every generator, appears at most twice in the relation. You see, it appears exactly twice. And that's what allows you to use a presentation theory very effectively. It's not the only thing, but that allows you to use a presentation. So as soon as I have here a word where one of the letters is used 3 times, the current methods seem to, we don't know. But Michael tomorrow is going to give a talk which explores much more in much more detail when you might hope to have, or what groups you may hope to have strong convergence systems. Come tomorrow morning.